Hello viewers, I welcome you all to my own YouTube channel. Today is the second lecture of P-block group 13. So we'll start uh, with the difference between boron and aluminum. Actually, actually, 80% of the chapter is done in this difference. Actually, the difference is most important. Actually, so the uh, difference lies like that: boron and aluminum. So first one is that boron is a non-metal, non-metal generally. So aluminium is a metal. So this is the most basic difference. Number two, boron is boron has a melting point of 2300 degree centigrade. Aluminium has a melting point of 600 degree centigrade. Now number three, it is 600 degree centigrade. Boron shows allotropy. Okay, it can exist in two forms. One is crystalline, and another is amorphous. Number three, aluminium can't show allotropy. Aluminium can't show allotropy. Okay. Now, number four, boron does not react with dilute HNO3 or dilute H2SO4. Aluminium react with dilute H2SO4, but it is not reactive with HNO3. Next one, boron oxide. It is known as boron anhydride. Boron anhydride is acidic in nature. Suppose B2O3 plus sodium hydroxide, it will produce NaBO2 plus H2O. Okay. Aluminium oxide L2O3 or alumina is amphoteric in nature. Actually, it reacts with both L2O3 plus NaOH produces NaAlO2 plus H2, or L2O3 plus HCl. This will produce AlCl3 plus H2O. This is also H2O aqueous condition. Aqueous condition. So this is the reaction with both acid and bases, but B2O3 can sometimes act as a basic oxide, because I'll give the reaction to you. This will be like that: B2O3 plus P4O10. This will produce BPO4. So in this reaction, this is this is sorry, this is a acid. This is a basic oxide. This is an acidic oxide. So uh, in this case only, or whenever reaction with AS4O10, then B2O3 will act as a basic oxide. So these are the 5 different answers. The next one. Next one is like that. Number 6. The hydroxides of boron are mild acidic, such as H3BO3. The hydroxides are amphoteric. Number 7. Boron does not show +3 electrovalency in the solid or liquid form, but aluminium is boron. Aluminium uh, does not show electrovalency in the solid phase, but shows +3 electrovalency in the solution phase, such as we have seen in the previous video, NaAlH2O whole 6 3 sodium hexahydroaluminate. Uh, okay, this one boron does not show +3 electrovalency in the solid and liquid form. It only shows +3 covalency. Okay, this is number 7. Now number 8. Boron hydrides are mildly stable, though undergo spontaneous burning when exposed to air. Alanes, boron hydrates are called boranes. These are called boranes. Hydrates are called boranes. Alanes, aluminum hydrates such as AlH3 are called alanes. Alanes are unstable, more unstable than boranes, and can be found in traces. Number 9. Number 9. The halides, the halides of boron are gaseous in nature, such as BF3, BCl3, etc. Number 9 here. The halides of aluminium are solid in nature. Though there is a trend, you can write down as a note here, that uh, that the boron halides are Lewis acids. The trend is Bi3 is greater than BBr3 is greater than BCl3 is greater than BF3. This is the Lewis acidic strength. Okay. Now the order is BF3 is greater than BCl3 is greater than BBr3 is greater than the BBr3 greater than Bi3. So this is the expected strength, but this one is wrong actually. This one is actually wrong because we will explain it later. So this is the number 9 difference. The number 10. The halides of boron are monomeric in nature. This is because you can see that BF3, BCl3, etc. They are aluminum halides. Aluminum halides are dimeric or polymeric in nature. I'll give you some examples here. Al2Cl6, Al4, F12. Now you can see the structures here. Aluminium, this is structure. This is because there's an important note. You can write it down here. The smaller size of fluorine and the electronegativity is responsible for this kind of structure. So this is number 10. We can find out many other properties also, such as next one. You can see number 1, boron. 11, number 11. Boron does not generally react with non-oxidizing agents, but aluminium does. The next one you can see number 12. Boron in the crystalline form does not generally react with air or oxygen. Number 12, aluminium reacts with oxygen in the moist form. Number 13. Number 13. Uh, Boron does not show +3 electrovalency, but it shows +3 covalency. Aluminium can show +3 electrovalency in the solid form, but it shows +3 electrovalency in liquid phase. Okay, the last one, then the next one, last one. Number 14. Boron forms borides. Aluminium forms alloy. such as you can see as boride Mg plus B, it will produce Mg3B2, magnesium boride. Magnesium boride. This is a very important difference between boron and aluminium. Aluminium forms alloy, alnico. Okay, so these are the difference between boron and aluminium. Now we are seeing about the diagonal relationship between boron and silicon. Number one, this is the similarities or diagonal relationship. Okay, this is the diagonal relationship. Okay, now what happens? Now we write down the similarities first. Okay, the melting point. The melting point of boron is near about 2300 degrees centigrade, but silicon also the melting point is near about 1500 degrees centigrade. So this is the first similarity, diagonal relationship. Number two, boron, this is the star. This one is a star. Boron forms borides and silicon forms silicides. Most important. Most important. Okay, now we write down the reactions here. Boron plus Mg, this will produce Mg3B2. Boron plus silicon, a magnesium plus silicon, this will produce Mg2Si. So this is known as the magnesium silicide, and this is known as the magnesium boride. Now the next one. Number three, both of the elements generally forms covalent compounds. Covalent compounds. Okay. Now you can see in case of this one, SiCl4. Okay. So this one is a covalent compound. Actually, there's a note here. There's a note here. CCl4. This is important for your school exams also. CCl4 is not hydrolyzed, but SiCl4 is hydrolyzed. Why? Hydrolyzed. This is because whenever you give Cl4 in H2O, this will produce SiOH, OH, 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 orthosilicic acid. But CCl4, H2O, no reaction. This is because carbon does not have any kind of vacant d orbital, but silicon have vacant d orbital. So silicon can extend its valency to +6, and carbon cannot extend its valency to greater than +4 is not possible. Greater than +4 is not possible. Okay, not possible. So carbon cannot extend its valency, but silicon can extend its valency. So it is a addition elimination reaction. First the water addition takes place, then the elimination of Cl occurs. So addition elimination reactions can occur in case of the silicon because it can extend its valency to from +4 to +6. So this is the third number difference. Number 4. Both of them shows allotropic, such as boron exists in two forms, crystalline, amorphous powder, crystalline and powder, and aluminium also in crystalline and powder. Silicon is also shows crystalline and amorphous in nature. Actually, silicon in the crystalline form have has higher melting point, okay, than the powder form or the amorphous form. Number 5, here you can see both the oxides are acidic in nature. Now you can see B2O3 plus sodium hydroxide, this will produce NaBO2 plus H2O. Now you can see SiO2 plus NaOH, this will sodium metaborate, sodium metaborate, NaOH, Na2SiO3 plus H2O, sodium metasilicate, sodium metasilicate. Number 6 number point is that their electronegativity is also similar. Actually, boron, I think, I'm not sure about that. Actually, I think boron is about 3.30 and silicon is near about 3.52. Okay, so these are the electronegativities of boron and silicon. Now, this is the diagonal relationship, and the proof of diagonal relationship is there. Now we are going through the chapter in details. We are now we are going to boron. Actually, the preparation, properties, and some reactions we will see. Now we will start the class as every element, each of their properties. Now boron. First, boron. We have to find out its preparation, properties, and reactions. Most of the reactions we have found in the physical properties and chemical properties. Now we are going through details. Now what happens? Boron is actually prepared from borax. Okay, this is the structure. This is the formula of borax. In the previous class, we saw the structure of borax. Now what happens? Na2B4O7 plus an inorganic acid, you can apply here H2SO4, HCl, etc. This will produce NaCl plus H2B4O7. Now what happens? Whenever this H2B4O7 is treated with water, this will produce H3BO3, orthoboric acid. Orthoboric acid. This is known as tetraboric acid. Tetraboric acid. Now, this H3BO3 is heated strongly to form B2O3, that is boron anhydride. Then B2O3 can be reduced by carbon or any other substance such as magnesium, such as sodium, etc. You can reduce it to boron pure plus CO2. Now, what happens? The boron here produced in the powdered form, so it has a purity of about 92 to 95% purity is present. Actually, this borax is found in the bottom of old lakes. Now this is the preparation of boron. You can also form the crystalline boron, but that is actually more difficult. Now what happens? This is the preparation of boron. Now in the difference between boron and aluminium, we found some of the physical and chemical properties. Now we are seeing details. Okay, now first we'll go through halides. Boron halides. Boron forms almost all kinds of halides such as BF3, BCl3, BBr3, and Bi3. Now what happens? All of them are Lewis acids because you can see the structure. You can see the structure. Now what happens? The octet is not satisfied. The 6 electrons are in the outermost shell. Now it has a deficiency of 2 electrons. Deficiency of 2 electrons are given here, so it will form a complex. So BF3 will also form a complex. Now what happens? The Lewis acid, all of them are Lewis acid, but the Lewis acidic character is like that. Bi3 is greater than Br3 is greater than BCl3 is greater than BF3. So this is the Lewis acidic strength of these halides. We'll see why this happens. Now we are seeing this. Actually, this is most important. Now you can see here. This is boron. This is fluorine. This is boron. This is iodine. So boron has a vacant p orbital. Vacant p orbital. Vacant p orbital. Now, what happens in this fluorine? This is a filled p orbital. This is vacant. This is filled. Now, what happens here? Back bonding takes place. Back bonding. So, what happens due to the similar size of the, this is actually the most important question in group 13. There similar size of the p orbitals, there is a partial overlapping of the orbitals, so the need of electron of boron decreases. Okay, now what happens? So it becomes less acidic. Less acidic. What happens here? The size of the p orbital is large in case of iodine. Now no back bonding occurs. No back bonding occurs. So the deficiency remains as it is. So highly acidic in nature. Okay, so this is the Lewis acidic strength. So Bi3 is more acidic than Br3, then BCl3, then BF3. Okay, now the next one we're seeing this. All the halides are monomeric. They can form complexes such as you can see here BF3 plus ammonia. This can produce this type of complex. Okay, okay. All the halides undergo reactions with NaH. What happens? BF3 plus NaH, it can produce NaBH4. So this NaBH4 is a reducing agent. So it can also produce, you can also see BF3 plus NaH. This can produce B2H6, okay, plus NaF as a product. So B2H6 has a structure of this B hydrogen, hydrogen, hydrogen. Here it is hydrogen, here it is hydrogen, hydrogen, hydrogen. So B2H6. Now this can also be done like that. BCl3 plus N okay LiAlH4. This will produce NaBH4 plus LiAlCl4. Okay, this is known as lithium aluminium chloride. This is known as lithium aluminium hydride. So today we are closing the class here. Actually, what happens in the next class? In the next class, we will see the uh, rest of the properties and reactions, and we'll see the aluminum preparation and its compounds. Actually, actually, two more classes are required actually to finish the lecture uh, or the series. So, if you find this video is important for you, you can please uh, give like and share my video, and stay tuned for the next videos. So, for watching the video, thank you to all. Goodbye.